So welcome to the RFIC course. So, this course will deal with wireless communication circuits. Okay, so first of all, the circuits will be slightly different from what you have seen before. They will all be narrowband circuits. They will not be wideband circuits. They will operate at very high frequencies. And there are some other characteristics that we have to ensure before they work properly. So first things first, about the course itself, this is a 9-credit course, 3 lecture hours per week. So as of now, we will meet on 3 of the F-slot hours, which are not at 8 o'clock. I think there is one at 8 o'clock on Friday, which we will not Friday. Yeah, the Friday we will not meet. We will meet the other F-slot hours. Okay. Number 2, I will add a disclaimer right at the beginning. This course is very project heavy. Okay, the theory, the circuits itself are relatively simple. Most of the learning that you will have is through building these circuits. Okay, so because of that, the project will carry most of the weight. Okay, for the grade, we will most probably have only one exam, which is the final exam. Okay, I will give practice problems. And periodically those practice problems will be evaluated as homework assignments. Okay. Apart from that, you will have probably 3 design projects in this course. Okay. Many of the design projects you can start only a month from now. So the first month, I will put out a tutorial for you to learn how to use a software called Eldo, which we will use for this course. I want you to spend the first month learning that. Okay, all the advanced stuff. Okay, because you're going to need it. Okay, each project will be, you will have about 3 weeks project. Okay, and if you, and there are no late submissions allowed in this course. So deadlines will not move. If I move any of the deadlines, you can forget about one of the projects, and that's not possible. Okay. So please make sure that you submit them on time, and many of these projects you cannot start at the last minute. Okay, so please remember that. So traditionally these are the 3 projects that you do for this course. So one is the low noise amplifier, that's the first project. Next is the mixer. Okay, next is the voltage control oscillator. We'll learn about each one of these circuits, and after we learn them, we'll assign the project and have you design them. Okay. This will be worth a substantial portion of the grade, probably about 60%. Okay, and the IMSEM will be 20%, and the assignments will be 20%. That you're looking at for this course. Okay, in case I make any change, I'll let you folks know. And as you can see, 60% of your grade comes from the projects. Pay attention to the design of the project. You can't do it in one day. You can't do it in 2 days. You'll need at least a week of sustained effort, probably 2 weeks if you're going to start from scratch. Okay. Textbook. So the textbook is titled RF Microelectronics. By called Behzad Razavi, and we will be the latest edition. I think it's from 2015 or 16. I'll put up the exact ISBN info, etc. on the class website and on Moodle. Okay. Okay, sounds good. So, first step, what does this course deal with? It deals with a wireless communication link. Okay. So you are dealing with circuits that implement a wireless communication link. Okay. And in most of these wireless communication links, it is normally the receiver that is tougher to build compared to the transmitter. So you will naturally see majority of courses that deal with communication circuits or RF circuits, they deal with the receiver. Majority of research happens on receivers. Okay, we will also look at transmitters, but we will focus on the receiver. Okay, and even in your projects, as you can see, the LNA mixer VCO will all go towards implementing a receiver. Okay, so what do I mean by this? So you have some digital baseband that puts out some bits, okay, some n-bit data, and you want to transmit this real time typically. It does not always have to be real time, but typically in a cellular communication, for example, it's real time to some other receiver. So you need to take this data, and because the wireless channel is a shared channel, you have to somehow separate users. Okay, you have to separate multiple users because several sets of people are trying to communicate with each other. And maybe in next class or after a few classes, we'll figure out the different ways in which you expect people to or you separate different users. But for now, let's assume that they are separate frequency. That is the easiest way to do this. So each user uses a unique frequency. Okay. Now the data itself will have a certain bandwidth. So let me call that some baseband bandwidth. Okay. So the data occupies minus FBB to plus FBB at baseband. Okay. Now if you try to transmit this data directly FBB, if everybody starts transmitting at FBB, you will of course interfere with each other, isn't it? So therefore, you need to find one unique frequency which will be occupied only by you. Okay, and so therefore you need to move this data to that frequency. Normally that is done through, I'm showing you the simplest possible implementation of a transceiver. In reality, each one of these can be broken up into multiple blocks. Okay, so but first, before you do that, okay, you have to use a digital to analog converter to convert that to analog, and then you upconvert that to some known frequency, to some desired frequency. I'm going to call that some FLO. Okay, if you do this frequency occupied at the output of the mixer basically moves FBB to FLO, okay, conceptually. So if this was the data bandwidth here, okay, what I'm going to do is move it around FLO. Okay, we will look at this in a little bit more detail, but this is what you're going to do with it. And then after this you might need an amplifier. Okay, so I'll show this. What do you do with this? You send this into an antenna which sends it to space. Okay, what happens to this signal? At some remote end, so let me call this the TX signal. It goes through the channel, wireless channel, it is received at some very remote receiver using another antenna, which converts the electromagnetic plane wave into an electrical signal. Okay, so this is your, so the received signal due to attenuation through the channel will be much small. Okay, you may see multiple copies of it through multiple paths, etc. Those are all things that you should expect, and imperfections of the channel itself. Now you have now received an extremely small version of what you transmitted. Okay, so if I look at the signal here, I get some very small version of it. What do I need to do? So I first need to, because it has become very small, I think many of you are also taking the analog ICs course, where we started looking at, how many of you are taking analog? Hopefully all of you. Any of you not taking the analog ICs course? Okay, only one person. So I think no problem. So in the analog ICs course we have started looking at noise. As you know, every circuit that you use has some noise. Today we saw it that it's characterized as an input referred noise. So imagine now the signal has become so small, in order of microvolts, let us say, and the noise of the circuit may also be of that order or only slightly smaller. You need to make sure that the signal is much larger than the noise itself. So first thing you need to do is send it through an amplifier so that the signal becomes as large as possible without adding while adding as little extra noise as possible. Okay. If you want the received signal to be as large as possible on the receive side, you need to transmit as large a signal as possible. Correct? Now, of course, there are certain limits. Many of these limits are, safety requirements. Right? You can't obviously blast out, electromagnetic radiation very close to where people live because people are jittery. Okay, about what this could do. Now, in reality, none of the cellular spectra that have been released are. Just 1 minute. Anybody have a pen that I could borrow? Okay, so can you just see here, there. No, press this way. Okay, so many of these things are set by coming back to this. The TX signal you want it to be as large as possible, but many of these things are set by safety requirements. Now safety can be in many forms. A lot of people are worried about things like cancer and so on. But we know from basic physics that only starting from ultraviolet radiation, you have enough energy to knock an electron out of its band into the next band, right? So naturally, if you expect DNA to get damaged, expect that to happen starting from radiation, starting from the ultraviolet region. Okay, unless all physics that we have, quantum physics that we have learnt is wrong, right? None of the cellular radiation should cause any type of effect such as cancer due to ionization of an electron. Having said that, obviously, lot of these frequencies are close to the frequency where water absorption of energy is very high. Your microwave oven, for example, works at 2.4 gigahertz. That happens to be very close to the frequency where water absorption is as high as possible from energy. That's why you use that for the microwave oven. Lot of your cellular frequencies are close to that. So you could indeed have local heating of tissue. Okay. In this case, the power is not as high as in a microwave oven, but in the microwave oven you are heating something for a few seconds or a couple of minutes. In this case, you are heating something, low grade heating for long periods of time. So naturally, you could have the cellular damage due to heating, okay, and then you have high turnover of cells, and therefore you could have safety constraints. Okay, therefore, if you take any wireless device, you will see that there are some specifications on how much energy can be transmitted per kilogram of body mass, etc. Okay, it is because of heating rather than any fears of DNA damage. Okay, but that itself is not very high, This is about a few tens of watts. Okay, so typically the transmit signal will be of the order of either watts to tens of watts, depending on what kind of system you're looking at. If you're looking at a mobile phone, which is always close to a person, it is typically hundreds of milliwatts to probably watts. Okay, this will probably be approximately a watt. Okay, if you take a base station, for example, okay, which is on top of a tower, that typically transmits tens of watts, 10 watts, 20 watts, 30 watts, numbers like that. Okay, they are typically slightly further away from the, but even this 1 watt is quite high. So this amplifier on the transmitter side is called a power amplifier. Okay, you are dealing with much higher powers. If you can imagine, 1 watt, okay, correspond typically to several volts of swing, several hundreds of milliamperes of current. Okay, which means that the current densities in the circuit, or the total currents of the circuit, of this power amplifier circuit, larger than what you have all encountered so far. So there must be something special about it, and power amplifier design is indeed a specialized area. Okay, that 1 watt, by the time it reaches your receiver, it is, it is attenuated by several magnitudes. Okay, several orders of magnitude. Okay, so by the time this 1 watt is received at the receiver, it is of the order of nanowatts. Okay, so which is why this amplifier is called amplifier here. This amplifier is going to add very little noise while adding gain. So this is called a low noise amplifier, or LNA. Okay. now that you have now increased the size of the signal, so now it is back to somewhat, it is not as high as it is at the transmit side, but it's much better. Okay, now what do? You now need to process the baseband signal at baseband, which means you need to go through one more round of changing the frequency through another mixer. And now what you receive here is basically okay, and remember that eventually you need to process it in the digital domain. So you go through an analog to digital converter and then back to the digital baseband for processing. Okay, so broadly, if you look at a wireless communication system, you can see that you need specialized circuits which are mixers. Okay, and you have on the transmit side, a mixer on the receive side, you have the power amplifier, you have the low noise amplifier, and what I have not shown here are the details on the LO side. Where does this LO come from? How do you generate it? That should also be very high frequency. So those are generated using specialized circuits called phase lock loops, okay, or frequency synthesizers. Okay, those will normally also come under the broad umbrella of RF. Okay, but if you teach time to teach the rest of the transceiver, so we will restrict ourselves to the so-called signal path. Okay, that is the LO path. What you do on the FLO side, on the receiver and transmitter, is the LO path. You will study more details about that in the phase lock loops course, okay, offered by Professor Saurabh. So broadly, we have come up with a very simple block diagram of the transceiver. Okay, so pretty much every transceiver which you see will have a transmitter and a receiver, and probably a synthesizer. The transmitter will have power amplifiers and upconversion mixers and some other associated circuitry, which we'll work out the details of what else is needed later. Normally the ADC and the DAC broadly come under a different circuits called data converters. They do not come under the umbrella of RF. Okay, because the constraints on those devices are different. They are mixed signal circuits, whereas many of these circuits, mixers, power amplifiers, LNAs, etc. are purely analog blocks. You don't have any digital content in the signal path, though that is changing nowadays. So we will restrict ourselves to these circuits. So we will study the mixers, low noise amplifiers, VCOs, and the power amplifiers. Okay, the VCO itself will go in the yellow path. We will restrict ourselves to only the VCO and not the PL. Any questions so far? Okay. So before we do that, some stuff at the system level. So we will also learn along the way what we need to know about this communication system. Okay. Part of that is how do you characterize the signal to noise ratio, how do you characterize the linearity, etc. Okay. Each different types of analog systems have different ways of designing those. But before all of that, we'll start with something very, very simple. So let us design a low noise amplifier. I'm going to look at the receiver. Where do I start? Normally the antenna itself is not part of the integrated circuit proper. It is a separate device because it is normally related, the size of the antenna is normally related to the wavelength at which you are operating. Normally the wavelength at which you are operating for communication, wireless communication, is so large, okay, typically it's in centimeters. What happens is that the antenna is too large to put on the IC. Centimeters is very large for the IC. So normally it's a separate component, okay, which does not reside on the IC. So we restrict ourselves starting from the low noise amplifier. Before we do that, as always, before you design any circuit, you need to know what is driving it. So we need to know the electrical equivalent of the antenna itself. So the electrical equivalent of the antenna, as far as this course is concerned, whether it's the transmitter or the receiver, okay, okay, in the case of the RX, it will be a 50 ohm resistor. In the case of an RX, so we will not distinguish between a receiver and a transmitter, okay, in the sense that for the receiver, we will replace the antenna by its electrical Thevenin equivalent. For you are receiving some received signal whose amplitude is VRX, okay, whose power is PRX, and impedance is 50 ohms. Okay, for some reason the standard impedance for all electromagnetic components for wireless applications is 50 ohms. Okay, so if you are doing anything related to microwave circuit design, everything is referenced to 50 ohms. Okay, in our case, inside the integrated circuit, we have the option of choosing any impedance that we want. Okay, but the minute you drive any other electromagnetic component, filters, amplifiers, anything outside your IC, they will all be referenced to 50 ohms. If you look at the input impedance of an amplifier, it will be 50 ohms. If you look at the output impedance of an amplifier, it will be 50 ohms. If you look at the input and output impedances of a filter, 50 ohms. Input impedance, output impedance of the antenna, 50 ohms. Okay, nominally 50 ohms. So if you had a receiver and this is going to drive your LNA, you can see that the Thevenin equivalent is going to be 50 ohms in series with whatever received signal strength that you have. What about a transmitter? Maybe I'll draw it like this. What about a transmitter? In the case of a transmitter, see, remember that the same antenna is going to receive and transmit at all times. But the received signal is completely uncorrelated with the transmitted signal. So as far as the transmitted signal is concerned, you just short out the received signal source and you only have a 50 ohm impedance. As far as the transmitter is concerned, you look at it as an electrical load impedance which is 50 ohms. Does that make sense to everybody? Okay. So let us start with the receiver itself. Okay. Now you are trying to drive the receiver IC with an antenna whose Thevenin equivalent is some voltage source in series with 50 ohms. Okay. Now, the other thing you have to remember is that the antenna itself may not be very close to the IC. It may be several tens of millimeters away from the IC on the board, let us say on the printed circuit board. Which means, as far as the electrical equivalent circuit goes, you now have a transmission line of some certain length, okay, between the antenna and your circuit. So of course we know that transmission line have all transmission lines course. How many of you have not done a transmission lines course? It doesn't have to be dedicated transmission lines, but you must have studied transmission lines as part of some course. All of you have. Very good. So I don't need to worry about introducing transmission lines. What do you know about transmission lines? They will add delay, of course, to an electrical signal. If you send in something, you will get something else. They may add attenuation, right? Hopefully, if designed properly, you will see a constant group delay, right? Either way, for our case, as long as you have constant group delay around the band of interest, you are good to go, right? At this frequency, you are still FLO plus or minus F baseband. If you have constant group delay around that frequency, you are good to go. After this, you hit the LNA. Does the additional delay matter? Luckily not. The reason is very simple. You already have so much delay through the, through the air, that the additional delay you get by 1 centimeter of, you probably have like a kilometer to delay through the air for that the plane electromagnetic wave has travelled, okay, from the other transmitter, from the remote transmitter. This extra, transmission line of a few centimeters is not going to kill you, okay. But what can kill you, okay, which you know from transmission line theory, is the fact that if the transmission line impedance is not matched either at the source end or the load end, you know that you will have problems. What are the problems that you will have? You will see reflections, right? You can see reflections at both the source side and the load side. So first thing you need to do, okay, you need to make sure Zin here, okay, is 50 ohms, right? As a matter of fact, of course, Zin depends on ZL also, okay, and Z0 of the transmission line. So this should be 50, which means the Z0 of the transmission line is 50 ohms, and on the load side, the LNA better present a 50 ohm input impedance. Does it make sense? If this were not true, so first of all, let us say the impedance looking in and on the source side of the transmission line was not 50 ohms. The first thing that would happen is you would see a reflection of the received signal. Okay, what does that mean? The received signal would go back, get re-radiated through the antenna. Right? Okay. If that happens, there are several unwanted scenarios. So for example, you might have a nearby reflector which could cause the signal to get reflected and come back again. Okay, which could then add destructively with your original received signal. That is a possibility. You could get multiple copies by a certain time. That is also possible. Okay, so you normally don't want that. The second thing that could happen is that the signal travels all the way through the transmission line, okay, and then gets reflected on the load side and comes back. That will add even more delay. That is also an unwanted phenomenon, okay. And if you see reflections, you can now see that you have heard of standing waves on the transmission line, right? When you have completely mismatched scenarios, okay. So the minute you have standing waves, what do you know? You know that the instantaneous amplitude of the voltages and currents can become very high. You can see unwanted scenarios such as electronic devices, Okay, these are all things that you want to avoid. Okay, so what you want to do, you want to make sure every component in the signal path is nominally matched to 50 ohms. So normally if you have a transmission line from the LNA to from the antenna to the LNA, that will be a 50 ohm transmission line. It is designed to have a characteristic impedance of 50. What is the characteristic impedance? You remember that there are per unit quantities L and C for the transmission line. Root of N over C is the characteristic impedance. Okay, that should be 50 ohms. Okay, if the transmission line is lossy, you will see further attenuation of the signal. Okay, so the signal which is already small becomes even smaller. So you need to make sure this is not very lossy. Okay, then now you see that your LNA is also present 50 ohms. So you need to figure out a way to make your circuit, your amplifier circuit. So now you see, unlike every other amplifier that you have seen, which normally has high input impedance or very low input impedance such as common gate, you now need a circuit that has something in between. It requires a 50 ohm. Whether it's a common source, common gate, whatever structure or source follower, whatever you choose, it better have a 50 ohm input impedance. Otherwise it's not going to work well. Okay? But your circuit itself may work very well when the impedance is not 50 ohms, but it may be 100 ohms. Right? What will you do then? So then you need to come up with specialized circuits that are going to transform impedances from one level to another. So in other words, your LNA may work best if your input impedance is 100 ohms, but your transmission line clearly requires 50 ohms. So very often you need what are called impedance networks. Okay. So what you are going to do is you are going to match this 50 ohms to something else, or maybe the power amplifier is going to require, it's better different impedance. So you need to match that impedance to 50 ohms, etc. Okay. So now these are relatively straightforward circuits. They are purely passive. They are relatively straightforward circuits. So starting from the next class onwards, we will start looking at these impedance matching circuits. First we will start off with resonant circuits, and then we will see how they lead to impedance matching circuits. Okay. Today's class I'll stop. Okay, I'll stop now. Tomorrow we have a class. Or tomorrow is a holiday, so Thursday we have a class. Right? Okay, so we'll meet on Thursday's class. We'll start with resonant circuits, series resonance, parallel resonance. Then we'll move on to impedance matching networks.